catch some of the chatter. Akram, hi.
Yes, now I can hear you. Yes.
Quick thing, did you do the Google form for the
Yeah, I did
course?
it this morning. Yeah.
Okay, great.
Yeah.
Kyle, you ready? Kyle, are you good?
Yeah. I'll go ahead and start.
Okay, so yeah, welcome back, Kyle, for part 2, and go for it.
Okay, thanks. So, yeah, this is part 2 of a talk I started last week, and so if you recall, the main theorem. Sorry, let me back up. So, this is joint work with Palaceto, Marcagola, and Alan. I should not forget to say that again. And so, the main theorem, what we want to do is we want to classify which positive integral surgeries on positive torus knots bound rational homology balls. So classify which of these 3 manifolds bound rational homology balls. So this is the goal. Now to do this, of course, you need a constructive element and an obstruction, right? So the surgeries that don't bound rational homology balls, we have to obstruct this. We have to prove that they don't bound a rational homology ball. And those that do, well, then we have to actually construct the rational homology ball, right? So there's these 2 aspects. Classification involves a construction and an obstruction. And most of today will be spent discussing this obstruction. And depending on how fast we go, which I'm not intending to go particularly fast, then perhaps we'll have a chance to talk about the construction side, or at least for one of these families. So this is where we basically ended last time. So what's special about surgery on torus knots are that, well, in particular, they're cipher fiber spaces. So these can be described as cipher fiber spaces. Here are the ciphered invariants. And remember that Q star, this is the inverse of Q mod P. And P star is the inverse of P mod Q. This is a rational surgery diagram for a cipher fiber space. And notice that, as we mentioned last time, this can be converted into an integral surgery diagram where we take the continued fraction expansions of these rational numbers and then turn this single component into a chain of unknots, where the coefficients on the chain of unknots will be integers representing the coefficient, the continued fraction expansion of these rational numbers. But the advantage of that is that not only does it describe, so it's an integral surgery diagram, so not only does it describe the 3-manifold, but you can also interpret it as a 4-manifold, as a Kirby diagram. And these are plumbed 4-manifolds, and it's often convenient to represent these in a plumbing diagram. So this is a corresponding plumbing graph associated to such a 4-manifold. If you recall, these surgeries break up into 3 cases depending on the surgery coefficient. When n is equal to PQ, this is a sum of lens spaces. When n is PQ plus or minus 1, this is a lens space surgery. And remember, both of those cases were covered by Liska, right? So Liska has a complete classification in which lens spaces and which sums of lens spaces bound rational homology balls. So that part of the argument is a bookkeeping one where we just consult Liska's list.
Say again, when do you get lens space and when do you get sum?
Yeah, so if it's PQ surgery, then this is a connected sum of lens spaces. In fact, I just looked this up, right? This is P minus Q, connect sum L, Q minus P. And if it's PQ plus or minus 1 surgery, then we get a lens space. And well, I could consult it, but let me not tell you which one. But so some lens space depending on P and Q. So this is a lens space. And then, so what's left is the situations where n is not in either of these, right? So, and there's 2 situations, right? So n could be less than or equal to PQ minus 2, or it can be greater than or equal to PQ plus 2. And these are analogous arguments. They're not identical, but they're similar. And so today I'm just going to focus on this particular case when n is less than or equal to PQ minus 2. So in this case here, the corresponding plumb 4-manifold is given by this graph. Maybe let me erase so this is not crowded. Okay, so we have this plumb 4-manifold, and A1 through AN, this is the continued these are the integers in the continued fraction expansion of P over Q star. And P1 through Bm, this is the continued fraction expansion of Q over P star. And we also have a chain of 2s where there are PQ minus n minus 1 2s. So all this comes from these Seifert invariants. So if we take these Seifert invariants and we convert it into a plumbing, this is what we get in this situation. Okay, so importantly, this the corresponding 4-manifold, which is a plumbing of disk bundles over spheres, is a positive definite. And so we can now introduce the obstruction. So if P of gamma denotes the corresponding plumb 4-manifold bounded by the surgery on the torus not TPQ, if the 3-manifold in addition bounds a rational homology 4 ball, right? So this is where we're setting up our obstruction. Then we can form a closed 4-manifold by gluing the plumbing and the rational homology ball together. So this is, we'll call this X. This is a closed 4-manifold, and we can assume that it's smooth, right? So everything, I haven't mentioned this, but we're working in the smooth category, right? So we're assuming that this is a smooth rational homology ball. Okay, well, the plumbing is definite, and that's going to force the intersection form for the closed 4-manifold to also be positive definite. And that's because, well, rational homology balls have a trivial intersection form. And so we get a closed smooth 4-manifold whose intersection form is positive definite, and hence we can apply Donaldson's famous theorem. So by Donaldson's diagonalization theorem, this intersection form QX must be isomorphic to the standard positive definite form. Okay, so this is using this big result of Donaldson, and what this tells us is that the lattice associated to the graph gamma must embed in the standard definite lattice of the same rank. Okay, so this is the first time I've used lattice in this talk, right? So lattice is just a free abelian group with a symmetric bilinear form. And so for low-dimensional topologists, you just want to think of the intersection form for a 4-manifold, which is a symmetric bilinear form on H2, where if there's torsion, you want to take H2 mod torsion. Or you could think of the intersection form for this plumbing embedding in the standard positive indefinite form. And this is our obstruction, right? So if the 3-manifold bounds a rational homology ball, then we have this lattice corresponding to a plumbing. And by Donaldson's theorem, this lattice must embed in the standard definite lattice of the same rank. And so if there is no such embedding, then the 3-manifold does not bound a rational homology ball.
So just let me ask, thinking about lattices again. So is it also correct to say, so the standard positive definite form, that's basically just, I can just think of that as z to the n with the, you know, just the actual standard lattice in Rn, right? You know, like the length of a vector, the inner product of a vector is the action of two vectors is actually the Euclidean inner product when I did just happen to be integer valued vectors, right?
Yeah.
And then embedding then literally means like finding some collection of subvectors in there that span a smaller dimensional lattice that have those where the actual dot products between them in the Euclidean thing actually give the intersection form I have, right?
So is it a smaller dimensional or maybe not necessarily have one?
Okay, yeah, so it's the same, it has the same rank, right? So
Same rank, right?
Yeah.
Not a lower.
Oh, right. Oh, right. Of course, not lower dimensional. Yes. Yeah.
So here's the intersection form for our plumbing, where n is the number of vertices in the graph or the rank of H2. And this obstruction is that there should be an embedding.
Right.
What this means is that, you know, if we have two elements here, right? So if I look at Q, B, gamma, say of A, B, that first I can map A and B by phi, right? So this is like phi of B, phi of A transpose. And then we have the standard definite lattice where, you know, in the standard basis is represented by the identity matrix. And so this is what we mean by an embedding into the standard.
So how about an example of an image in there?
Yeah. So thank you. So that's the next slide is I want to look at some examples. So let's look at these examples, and then I'm happy to come back and discuss, you know, a more general perspective as well. But so this is actually important because I really want to highlight that, you know, the advantage. So it's a powerful obstruction. It's quite useful, but it's also very tangible, right? So this is what I want to illustrate here is that you can actually get your hands on this. You can use this obstruction. So I want to look at these two examples, right? So I have two surgeries on torus knots. The first one is 49 surgery on the 317 torus knot. And the second one is 16 surgery on the 37 torus knot. So I've already computed the corresponding Seifert invariance. And then from the Seifert invariance, I've written down the corresponding plumbing graphs. So these are the plumbing graphs for these 2-3 manifolds. They're positive definite. And the obstruction says that if, well, let's look at this first one first. So if this 3-manifold bounds a rational homology ball, then the lattice corresponding to this plumbing should embed in the standard lattice of rank 6. So we're wondering, does this embed into D6 with the identity matrix as the intersection form? So this is what we're wondering. And for this standard lattice, let me just represent the standard basis vectors by EI, right? So we have E1 through E6. And so from this perspective, what does an embedding look like? Well, each vertex corresponds to a generator of H2 of the plumbing of the plumb 4 manifold. And I should tell you, where does this generator get sent under this embedding in terms of these standard basis vectors, right? So I have to tell you where a generator corresponding to each vertex gets sent to in E1 through E6. Let's look at this first one here. So this vertex has weight 2. This means that the corresponding generator for H2 has self-pairing 2, or squares to 2 under the intersection form. So this should be sent to some element here that has squares to 2 under this standard under the standard form. And it turns out, well, there's not very many of them, right? So the only elements here of square 2 are sums or differences of exactly 2 standard basis vectors, right? So for example, I could send this element to minus E5 plus E6, or E2 minus E4. Of course, I could just reorder the basis vectors. And so up to reordering the basis vectors or perhaps changing sign, I can send this one to E1 plus E2. And again, up to reordering the basis vectors or changing the sign, this is the only choice I have, right? So it has to be something of this form. And so whatever 2 basis vectors I send to, I'll just call them E1 and E2. Okay, so well, the same analysis goes here, right? So this, the generator corresponding to this vertex should be sent to sum or difference of 2 basis vectors. But the fact that there's an edge connecting these 2 vertices mean that these 2 elements, they square to 1 under the intersection form, right? So what that means is that, well, this vertex here should be sent to something in here, but it should have either E1 or E2. Right, and not the other. And again, up to reordering basis vectors, I can choose to send this to E2 plus E3. Now let me pause, right? So if you're okay with this, then this is the hard work, right? So up to reorder.
So Kyle, just to suppose I stop there. Suppose I just had the plumbing graph with 2 2s and an edge between them.
Yeah.
Then this is showing me that I couldn't do that, right? Because I'd have to have E1 plus E2, and then I have to have E2 plus E3, and then but I don't have an E3 because I need.
Yeah, exactly. And so, I mean,
so that lattice with that plumbing with just 2 2s and an edge between them does not embed in the standard lattice.
Yeah, exactly. And in fact, this is a proof that the length space L31 does not bound a rational homology ball.
Ah, okay, cool.
And in fact, this is really a key point, which is that chains of vertices with weight 2, they embed into the standard lattice, but you need 1 additional basis vector than you have vertices, except there's an exception when you have 3. If you have 3, a 2 chain of length 3, then there is an embedding. This corresponds to the fact that the length space L41 does bound the rational homology ball. But important there is that if you have a chain of length 3, it can't be attached to anything else. So here we have a chain of length 3, but it's attached to 2 other vertices. And so this special embedding, which, unless you force me to, I won't say anything more about, doesn't come into play. And our 2 chain is just going to be forced behavior like this. So for example, the next one will be sent to E3 plus E4. And then here we'll send this to E4 plus E5. And up to reordering the basis vectors, we have no choice involved here. Okay, so on the 2 chain, we're forced, and the other, we have 2 more vertices. In fact, there is an embedding here. So let me describe the embedding for the vertex of weight 3. So there's an edge connecting it to this vertex, so I should have either E3 or E4. It turns out E4 is the one we want. But notice that E4 appears here. And so unless I counterbalance this with something with E5, there should be, an edge here, but there's not. And so in order to preserve orthogonality, I should put a minus E5. So this minus E5, I preserved the orthogonality between these 2 vertices. And I need 1 more basis vector to get weight 3. And luckily, we have 1 more available, right? So E6 is available. And so this describes an embedding of this plumbing so far with everything except this last basis vector. It turns out there is an embedding here. Let me just write it down. And if you want, you can check that I'm not lying. So I send this vertex to minus E1 plus E2 minus E3 plus E4 minus E5 plus E6. And so this has the required properties, right? So it has weight 6. It pairs once with this vertex, right? So we have E4 minus E5, minus E6, sorry. So it pairs once with this vertex, and then it's orthogonal to everything else, right? So we have an E4, but we also have a minus E5, so it's orthogonal to this. We have E3, but we have a minus E3 and a plus E4, so it's orthogonal to this and so on. So this describes an embedding into the standard lattice of rank 6. And so in other words, the obstruction fails, right? So for this example, the obstruction fails. And it turns out, as you might expect, given the claim that we're given a classification, that this 3-manifold does in fact bound a rational homology ball. And again, given the time, I might be able to give you the construction, right? So there is a corresponding construction that shows that this manifold does in fact bound a rational homology ball.
Do you know if just the algebra here proves that it bounds a topological rational homology ball?
Yeah, that's a good question. I'm not sure. So the algebra, in fact, gives a suggestion on how to construct the rational homology ball, even in the smooth case, but it requires an additional argument. In the topological case, I'm not sure. Okay, so that's this first example, and let's look at the second one. Notice that we have a very long 2-chain. And so if you were convinced by my discussion previously, so on this 2-chain, we'll have the same sort of phenomenon, right? So let me just give the embedding here. Up to reordering basis vectors, it's going to look like E1 plus E2, E2 plus E3, E3 plus E4, 4 plus E5, 5 plus E6, E6 plus E7, E7 plus E8. And let's see, we're trying to embed into the standard lattice of rank 9. So we've used all but one. We still have one additional basis vector to use. And I can embed this bottom vertex, right? I can send this to, say, E6 minus E7 plus E8. But there's going to be no embedding of this last vertex. So even though we have an additional basis vector, it's not going to help us, right? And we can make an argument. And so I'll just sort of outline how the argument would go. Let me use a different color. So
are you telling us at this point that there really wasn't much choice on that E6 minus E7 plus E8?
It turns out there's not, right? So we have to have either E6 or E5. And if you have E6, well, then you have to be orthogonal to this vertex. So you have to have a minus E7. And then you have to be orthogonal to this vertex. So you need a plus E8.
But couldn't you go backwards and do plus E1 minus E2?
Yeah, so, or you could have E5, right? But if you have E5, then you need a minus E4, and then a plus E3 to be orthogonal here. And then you need a minus E2, and you're already have weight greater than 3. So this has weight greater than 3, and so it's not allowed. And in fact, this is essentially the argument here, right? So for this last basis vector, we either need E7 or E8 because they're connected by an edge. Let's say we start with E7. So if we have E7, well, then by orthogonality, we have to have E6. And then again, we have to have all these basis vectors because we're orthogonal to all these vertices. And so it's going to be minus E6 plus E5 minus E4, and then already we're too big. So the weight's too great. The only other option is we start with E8. Let's see what happens if we start with E8. Well, E8 appears here, and we're orthogonal to this vertex, and so that means we need either E7 to preserve orthogonality, or we need E6. Notice that we already covered the case when we have E7 here. And if we have E6, well, it's the same problem, right? So we have E6, but then, well, in fact, we need E7 as well, but you need E5 and E4, you need all these basis vectors. And the weight will be bigger than 3. And so neither of these are viable. And this is proof that this lattice does not embed in the standard lattice of rank 9. So in other words, the obstruction applies. And so this argument here implies that this manifold doesn't bound rational homology ball. So any questions on the obstruction more generally, or these examples?
Well, I guess how far afield would it take you to show me the L41 case? Because I feel like, you know, this example shows, you know, is like all that can happen. So what could be special about 3?
Okay, so in 3, so notice that here we started with E3 and then we added a new one. But instead of using E3, I can use E2. But that creates a potential problem, which means I need to still be orthogonal here, but that's okay. I can just put in a minus E1. And so this is an embedding of a lattice where we have a 2 chain of length 3 into the standard lattice of rank 3, right? We're only using 3 basis vectors.
I see. But if you try to continue that, then to do a 4th one,
So
you'd have to use E1 or E2, and then you'd be stuck.
Yeah, so suppose there was some other basis vector here. Well, then you're going to have trouble, right? So either you need either E1 or E2. If you have E2, well, then you need a minus E3. But then you also need to be orthogonal here, so you also need a minus E1. But then we now this is actually messed up. Now we actually, you know, pair twice with this, right? So in fact, there's no.
Yeah, no, I get that. That's good.
So
Thanks.
there is this special embedding if you have a 2 chain of length 3, but then it can't be extended to any other vertex. Certainly not if we have a 2 chain at least. Other questions or comments? So if you haven't seen this sort of analysis before, then, you know, it might seem, you know, perhaps convoluted, but I want to emphasize that, you know, once you do a few examples, you start getting the hang of it, and it's really something that you can work with, right? It's actually not hard to either construct an embedding, as in the first example, or prove, even if the, you know, a full proof might be a bit, you know, involve lots of different cases, but you can prove that a given lattice does not embed in the standard lattice of the same rank. Now the trouble becomes is that, well, so this is a proof for a single, you know, a single manifold, but we're trying to cover all possible positive integral surgeries on positive torus knots. And so somehow we have to deal with families. And the analysis is much more complicated if you're trying to show a whole family doesn't embed, right? You can't actually write out the specific plumbing and then show that that specific plumbing doesn't embed, right? We can't do this for infinitely many plumbing. And so therefore the question is, well, how do we actually proceed? And so
can I ask you something? I'm having this crazy memory. So Donaldson's theorem I know works for simply connected manifolds.
Yeah.
Is this obviously simply connected, or does it work more generally?
No, so, you know, if we're assuming that a rational homology ball, when we glue together, it's not going to be simply connected. But
right.
But Donaldson had a follow-up paper where he removed the simple connectivity hypothesis. So okay. I think in his first paper,
and it was completely removed.
Yeah, that's my understanding.
Huh. Okay. Yeah. Okay.
So are the fundamental group always finite in these kind of manifolds?
I mean, it was somehow really important that there were no reducible connections. I don't know. I'll think about it. I'm being stupid.
Yeah. So yeah, my understanding is that a later paper removed that. I mean, maybe it depends on the actual application, but
okay.
Yeah. So we're not assuming anything about the fundamental groups of these closed form manifolds.
Right.
Okay, so well, this is the most technical slide for today, and actually, let me sort of gloss over the details for the sake of time. So again, remember the point is that we need to get a hold of, you know, these lattices so that we can make arguments about whole families. And importantly, we're not considering arbitrarily arbitrary three-legged Seifert fiber spaces or three-legged plumbings, right? These are plumbings that come from positive surgeries on torus knots. And so, you know, what in here is special about this situation? And it turns out that there are a couple things. One, we have this two-chain leg, and then these weights are not arbitrary, they're actually related in a special way. And so this text makes the argument, but let me just sort of give you the punchline. So if I call this b minus 1, then we'll have one more vertex with weight k plus 1. K is the floor of q mod p, but I don't think that's particularly important given that I'm just giving you the punchline. And then we have these two strings of integers, b1 through bn minus 1 and a1 through an. These are going to be what are called complementary strings. What that means is that if we take their continued, if we take the corresponding rational number, say a over b, right? So these represent continued fractions of some rational numbers a over b. If we take the reciprocals, then they add up to 1. And so that's actually highlighted down here, right? So if we take 1 over the rational number represented by a1 through an and 1 over this continued fraction, then they add up to 1. So this is the definition for being a complementary string. It happens to have several nice properties, and I think one or two of them I'll mention. And so this is actually what we're working with, right? So we have a lattice, it's not arbitrary. We have a two-chain leg, and then we have, well, this one extra vertex, and then we have these two strings which are complementary. And this is what we have to study. And so the strategy then becomes to study the embeddability of such lattices into the standard lattice of the same rank. So recall last time I mentioned that Paolo Aceto and Marco Gola had previously studied the case when Q is congruent to plus or minus 1 mod P. And so this is a simplification. The reason why it's a simplification is that in this scenario, one of these continued fraction expansions is corresponds to a two-chain. So if I look at this picture here, one of these strings is just going to be a two-chain. And so that together with this two-chain gives us a very big two-chain in the plumbing. And in fact, these examples fall into that scenario, right? So look at this example here. So here, Q is 7 is congruent to plus 1 mod 3, and we get this very long two-chain. And as we saw here, that this two-chain has a very restricted embedding. And so if we have a big two-chain, then it gives us a restricted, it really cuts down the possible embeddings, and this makes a much easier analysis. So if we have a long two-chain, then we get, provides a strong and relatively straightforward obstruction. So that was why they assumed this condition, right? This is why it was a simplification. When Q is not congruent to plus or minus 1 mod P, then the analysis becomes more difficult. And I want to tell you a bit about the strategy. So the strategy has to do with this quantity I. So for any weighted graph gamma, I of gamma is defined to be, well, we take the sum over all vertices, and we take the weight of the vertex, right? This is so vi squared, this is the weight of the vertex, minus 3. So it's sort of a mysterious thing to define. It appears in the work of Liska, and I'm just saying that we had some discussion in the chat about Donaldson's work. Okay.
Yeah, it is. It's like done in 87, right?
Okay. Well, thank you.
Yeah.
Okay, so this quantity appears in Liska's work, and the way you should think about it is that the more negative I is, the harder it is to embed into the standard lattice of the same rank. And the reason why is that, so in this context, we're assuming that the weights are always at least 2. So we have some plumbing, the weights are all at least 2. And so the only way this can be negative is if we have a vertex of weight 2, right? And that means this would contribute minus 1. And so the more negative I is, that means the more 2s there are in our lattice. And we saw that, these weight 2 vertices have restricted embedding. So the more negative this quantity is, the harder it should be to embed into the standard lattice of the same rank. Okay, so we can actually compute I of gamma for our plumbings, and here we use that we have these two strings, these complementary strings. So if we have a graph that consists of two linear components with weights given by complementary strings, then you can check that I of such a graph is -2. And so if you look at our plumbings, we can now compute I. So we have these complementary strings. These contribute -2 to I. We have this vertex with weight k plus 1. This contributes k minus 2 to I. Then we have these this two chain. And each vertex in the two chain contributes a -1. Plus we have this central vertex. So these all contribute -1. And so we can calculate for our graphs, we have that I is equal to -2 plus k minus 2 minus quantity r plus 1, where r is this length of the two chain leg. And so we have this calculation, k minus r minus 5 for I for our plumbings. And it's actually important for the argument, but let me just say in passing that we can show that k is less than or equal to 7. And so you could think of this as an upper bound. So we've bounded I from above. In fact, we have an exact calculation, but depending on r, we have an upper bound using that k is less than or equal to 7. So what we want to do is provide a lower bound if we have an embedding. And for that, we need the following idea.
Hey, Kyle, I just spaced and lost track what k is in this formula. Just
Oh,
remind me.
Yeah. So k is this weight here. So
Oh, okay.
we have these two complementary strings and then this one extra vertex with weight k. K is the floor of q mod p,
Okay.
but that's not that important.
All right.
Okay, so we have the following idea. So we have a calculation for I, but suppose we have an embedding into the standard lattice, then we can use this embedding to calculate I in terms of the standard basis vectors. So if we have an embedding, each vertex can be expressed as a linear combination of the standard basis vectors EI. So here, alpha ij, this is the coefficient of the standard basis vector EJ when in the embedding of the ith vertex. So we use this to compute I another way. So here's the definition of I. But now we use this embedding, right? So the weight of the ith vertex or the self-pairing of the corresponding element in the intersection form is given by the sum of the squares of these coefficients. Okay, and so I and j, well, these range over the same index set, and so we can permute the order of summation, and we get this expression here. And this is expressed purely in terms of the coefficients of the standard basis vectors in such an embedding. So, so what's the upshot? Well, the upshot is, well, how can a basis vector EJ contribute negatively to this quantity? So if we look at this expression here, the only way a basis vector can contribute negatively to I is if it appears at most twice with coefficients plus or minus 1, right? So only at most two of these should be non-zero for a given EJ, and it must have coefficient plus or minus 1. Otherwise, this quantity here would be greater than or equal to 3, and so we would contribute non-negatively to I. So this is an important point, right? So we're trying to bound this quantity from below, and hence we need to know, well, how can this become negative from this perspective? It can become negative in this perspective if we have an embedding where we have a standard basis vector that appears at most twice with coefficients plus or minus 1. And so the strategy then is that we want to study such vectors, and in doing so, bound I of gamma from below. And so, for example, one thing that's shown is that in such an embedding, no basis vector appears exactly once with coefficient plus or minus 1, right? So that, for example, is not allowed. And if standard basis vectors appears twice, then there's always some other basis vectors that compensate. So This is sort of a benign sentence, but this is really the meat of the argument, right? So this is one sentence, but this is 50 pages of very technical work by Anna Lipona. So it's much more, much more significant than a simple sentence would suggest. Okay, good. So yeah, like I said, so this is a 50-page argument, and we obviously don't have time to do that in 20 odd minutes, but I want to give you a little taste of what the arguments are like, right? So it's very technical, lots of different cases, and here is you could say sort of a nice part of it. So let me just discuss this lemma and indicate the sort of things that are going on in this argument. So it can be shown that for our plumbing graphs, an embedding has to take this form, right? So this is the two leg, and then these are the two other vertices that are adjacent to the central vertex, right? So we know two chains have a fixed embedding. Here you see it here. And since what's to the left and right of the central vertex, these are complementary strings, it turns out that one of these should have weight 2 and the other one should have weight bigger than 2. And it turns out this is the embedding has to take this form here. Okay, and so notice that if you look at the basis vectors E2 through ER plus 2, these all appear 3 times in this picture. So for example, E2 appears in the central vertex, this vertex here, and it also appears in the sum. And if you look at E3, well, E3 appears here, but it also appears in the vertex to its right. So I can stick another one here. This is going to be E3 plus E4. So E3 appears here, and it also appears here. So already each of these basis vectors appears 3 times, and the lemma says that they have to appear somewhere else, not pictured. So the lemma says that in such an embedding, these basis vectors E2 through ER plus 2 all must appear elsewhere in the embedding, and hence they contribute at least R to I of gamma, right? So again, the bigger context is we're trying to have a lower bound for I of gamma if we assume that we have an embedding. And this says that, well, if we look at the basis vectors appearing in the 2-chain leg, they contribute at least R. And R is the length of this 2-chain leg. Or, well, the 2-chain is, this part is R, and then we have the central vertex. Okay, so let's discuss this lemma. So by orthogonality, if one appears elsewhere, they all appear. And this is similar to the analysis that appeared in our examples. But let's suppose there's some basis vector, and let's suppose that, say, E3 appears here, plus some other things. Well, by assumption, this vertex is orthogonal to both of these. And so that means we have to have minus E4. So we have to have minus E4, and then we also have to have minus E2. But then if we have E4, then we have to be orthogonal to the next element, which has E5, right? So then, and like, oops, I don't know how that happened. So because this vertex is orthogonal to each of these vertices in the 2-chain length, we have to pick up all of these basis vectors all the way to ER plus 2. Okay, so that's the argument for this claim here, right? So if one appears elsewhere, they all appear, which is actually what we want, right? We want to say they all appear somewhere else, and therefore they each contribute positively to I. So by way of contradiction, let's assume that that none appear. So if none of these basis vectors appear elsewhere in the embedding, we can perform the following manipulation of our graph, plus embedding, in fact. So consider the graph with embedding obtained by deleting all these standard basis vectors. The resulting graph with S vertices is linear with 2 connected components. So if we delete all these basis vectors, all these vertices will disappear. And we'll be left with these 2 linear components, right? So we're deleting E1. So this vertex will now just be with weight 1 will be ER, and so on. And then here, this is this B prime. So we have these two linear components. And importantly, we have one more vertex than standard basis vector, right? So we have a graph with S vertices, but it now emits an embedding into the standard lattice of rank S minus 1. And that's because we've deleted one more basis vector than vertex, right? So we've deleted R plus 2 basis vectors, but we've only lost R plus 1 vertices. So we have this lattice here, and it embeds in the standard lattice of rank 1 less than itself. So it's a linear algebra exercise that means its determinant has to be 0. So if you look at, so if you think of this as a plumbed form manifold, right, its intersection form then would have to have a determinant 0, but this in fact is a contradiction, right? So such a lattice has non-zero determinant. That's because all these weights are at least 2, except possibly these final vertices. And so this is, something that's not too difficult to check, that under this circumstance, you can't have determinant 0. And that completes the contradiction. Okay, so I'm afraid that there were too many words there. Well, if there aren't any questions, let me at least mention briefly something about the constructive side. So this is all I want to say about the obstruction. It involves lots of similar arguments to this, right? So I think here I've just given you a taste of the sort of arguments that are involved. So let's turn in the last few minutes to the constructive side. In particular, I want to look at this one family. So last week, I gave you the whole list. This is one of these infinite families that appears that does bound rational homology balls. And it's defined using this recursive sequence. Now, admittedly, if described like this, it seems quite mysterious. Where does this recursive sequence come from? But it, in fact, comes from a family of plumbing graphs that all admit embeddings. So the corresponding lattice or plumbing graph is exhibited here. Notice that we have a chain of 6s where we have S here and then so one more, so S plus 1 total. And we have this block, so 1, 3, and 3 2s, and this is repeated S times. So if S is 2, then we have this block here plus another one before our final weight 2 vertex. And in fact, one of the examples previously was when S is 0. So actually, when S is 0, I constructed such an embedding. And the claim is that, well, there's this family of graphs, and they all have sort of related embeddings. So you can go from one, it's relatively natural to go from one to an embedding of the next one. So we have this family of plumbing graphs. They all emit embeddings into the standard lattice of the same rank. If you convert this to the PQ and the surgery coefficient, you get this recursive sequence. Okay, so we want to prove that these three manifolds do bound rational homology balls, and the following is the strategy. So we show they bound a rational homology ball by exhibiting an integral surgery from this manifold to S1 cross S2. So why does this suffice? So if there's integral surgery from this surgery on a torus knot to S1 cross S2, well, there's also the dual surgery that goes backwards, right? So that means there's also an integral surgery from S1 cross S2 to the three manifold in question. And since it's an integral surgery, this corresponds to attaching a 2 handle. So S1 cross S2, if we think of it as the boundary of S1 cross B3, we can build a 4 manifold by attaching a 2 handle corresponding to the integral surgery to S1 cross B3. So this is a 4 manifold with a single 0 handle, a single 1 handle, together giving S1 cross B3, plus a 2 handle. And the boundary is this surgery on the corresponding torus knot. Now it turns out that this 4 manifold we've just described has to be a rational homology ball. And this is just an exercise with the long exact sequence of the pair. So since the boundary is a rational homology sphere, that forces the 4-manifold to be a rational homology ball. In other words, this 2-handle has to kill the H1 here, at least with rational coefficients. So anyways, this is a fairly easy homology exercise. And this reduces the challenge to finding such a surgery. So how do we find such a surgery? And in 1 minute, well, in 1 minute, I'll just show it to you. So the claim here is that this curve in gray is the required surgery from the 3-manifold given in this this Kirby diagram representing the plumbing to S1 cross S2. So notice here that, and this is actually perhaps surprising, is that the claim is that this works for any member of the family. So notice we're only showing the components around the central vertex. So if you look at this plumbing here, we're only showing you this part of the plumbing. And the claim is it actually doesn't matter. Whatever else is left over, we still get a surgery to S1 cross S2. And the way you prove this is, well, you start blowing down. So if you blow down this gray component, then well, it's going to introduce some additional crossings here and also change the weight. So this component will now have weight 1. And we can blow it down. After we blow these 2 components down, then this component here, which originally had weight 3, will now have weight 1. It'll have gone through 2 blowdowns, so it'll have weight 1, and we can blow it down. And after 3 blowdowns, the claim is that we get this picture here, where the original, the component corresponding to the original central vertex now is this weight 1 guy. On the left, nothing has been changed, right? So this is still the weight 2 component. And here, this first 6 now has weight 3. And this is a surgery diagram for S1 cross S2. So here again, we use the fact that we have these complementary strings. So using the complementary strings. And so just go back to this picture briefly. So we've done a sequence of blowdowns, and we've changed this central vertex to weight 1. This guy is no longer here. Everything else on the left is the same. And we've gotten rid of this weight 3 vertex, and this first vertex with weight 6 is now a weight 3. Everything else is the same. So you can sort of think about what we did is we've gotten rid of this, and we changed this to weight 1, and everything else is the same as before. And now we have complementary strings, right? So now this on the left is complementary to this on the right. And it's one of the properties of complementary strings. If you put them next to each other with the weight 1 vertex in the middle, there's a sequence of blowdowns which terminates with a single vertex with weight 0, which is a surgery diagram for S1 cross S2. And in fact, you can see how it sort of starts, right? You blow down this guy. Now this vertex has weight 1, and this has vertex weight 2. You blow this down, and now this guy would have weight 1, and you go back and forth blowing down, and you terminate with a single vertex of weight 0. Oh, and that's all I have. So thank you.
Thank you, Kyle. Shall we clap? Questions? I was wondering, Kyle, if you know any contact / symplectic information here, or any of these fillings, or
Yeah, I don't know. I haven't thought about it at all. Perhaps my well, yeah, maybe there's something. So for most of these rational homology balls, we show that you can embed the trace of the surgery plus the rational homology ball. Well, in fact, glued together, you get CP2. So you often have embeddings into CP2, and that tells you whatever it tells you. Yeah, I think that's the only thing I could say.
So this thing you constructed as a 4-manifold, it's the B plus is very high, right? It's like
Yeah. So the plumbing doesn't embed. So the claim, if you're referencing what I just claimed, is that the trace of the surgery right? So, you know, you have, say, in fact, well, we didn't actually show it for maybe I can go to the beginning. So for example, I think for this family here, we show that all these three manifolds embed into CP2, where on one side you have the trace of the surgery, so just a zero handle plus the two handle. And on the other side, you have the rational homology ball. So you get that B2 is 1, as you would expect.
Yeah, so maybe, so I have a very basic question. What is the trace of the surgery?
Yeah, sure. So if you have an integral surgery on a knot, so here's the right-handed trefoil. Let's say you do 9 surgery on the right-handed trefoil. You can think of this as a surgery diagram or as attaching a 2 handle to the 0 handle with framing a 9 in this case. So the
Sure.
trace is this 4 manifold. It's the result of attaching the 2 handle to the 0
Oh.
handle. And the boundary is the surgery.
Okay.
So you were just saying that for some of these, at least, you know that the trace of the surgery embeds in CP2 so that the complement is the rational homology ball.
Yeah. And in fact, you know, some of these families appear in sort of that context, right? There's this. Let me. I wrote it down so I could say that more precisely. So there's this paper by Fernandez, de Bobadilla, Luengo, Mel Hernandez, and Nemeti. So they classify all rational complex curves in CP2 with one singularity of type PQ. And so this is, you know, it's the same question, but from the, you know, singularity point of view, right? So some of these were known to already embed in CP2 from the singularity perspective. So in fact, so this family does in 10, 18, 5, and some of 3. So all these surgeries actually appear in this context. And the point there is you have this, you know, rational complex curve, and a tubular neighborhood is actually going to be a trace of a torus knot surgery, this torus knot surgery. And for homological reasons, the complement has to be a rational homology ball.
So in those cases, it's probably the rational homology ball is probably actually a symplectic filling then of sum-induced context structure. I mean, if the singularity is, I mean, I'm just guessing. If it's all if everything's working symplectically and these are positive surfaces or something.
Yeah, and in fact, I mean,
We know that the trace of the surgery over here has a you know, convex or concave boundary.
So I'm just saying, I'm guessing from the singularity perspective that these traces have concave boundaries so that the complements are convex things with, you know, which are fillings of other balls. I mean, that's how it works with L41 at least, right? The lens that's the boundary of a neighborhood of a sphere of square. I mean, you know, of a
yeah. So there's this paper.
degree 2 curve.
Okay, I mean, in order for that to be symplectic, right, you have to have, you know, the TB, you have to be able to find the legendrization of the thing.
Well, what I'm saying, if it's all coming from algebraic geometry somehow, the ones that come from algebraic geometry, that probably automatically happens, I'm guessing.
So there's a paper by Stipchit, Sabo, and Wall, which, yeah, so if you have links of singularities, they study the existence of symplectic rational homology ball fillings of the corresponding canonical context structure. So yeah, I can't tell you exactly what they show, but yeah, they looked at this precise question.
Could you tell me again how these embed in CP2? Like, what did you take the neighborhood of?
Yeah, so, oh, you mean the singularity?
Right. So you like you write down some polynomial which like x to the p plus y to the q, which gives you a torus knot or something, and then that lives in CP2.
Yeah, so this is your, so, this is the, I was in Budapest for a couple years, so I should be able to draw this picture, but I'll probably fail there. So anyway, so this is your rational curve in CP2, and a neighborhood of the singularity. If you look at here, you see the torus knot TPQ here. And if you look at a neighborhood of this guy, you see, well, here this is just say you could, the neighborhood of the singularity is just a 4-ball, and then you see the torus knot on the boundary, and then this is like a 2-handle attached along the torus knot, and so this is two. And the complement for homological reasons has to be a rational homology ball, right? Because you've already captured B2 in this.
And is there any conditions on P and Q for this to be a rational curve, or is it always rational?
Yeah, I don't know. I shouldn't say something that I don't know is true.
So from this picture, it's not automatic that this boundary is concave or convex, because there are some kind of corners you need to smooth out, right?
Yeah, I don't know.
Any other questions? Okay, thanks, Kyle. Let's thank Kyle one more time. See you guys later.
Dave, I have an administrative question.
Okay, yeah. Here, I'll stop the recording. Wait. We'll embarrass ourselves.